Okay, we're running a 3rd horsepower motor, 2-pole, 3450 RPM on 115 volts. Okay, and testing a 3rd horsepower induction motor. No load, just running a grind disc. Got the input power is 131 watts. And it's drawing 3.4 amps at almost 120 volts. 60 hertz is the frequency. And the power factor is 0.32 on my meter. Looks like it's 60 hertz. What do we have here? 131 watts, 3.4 amps, 119.9 volts, 60 hertz. There's the power factor. So we got the volts times amps is high, the actual watts is not too much. Now, because it's running no load and you've got a big reactive component here, because it's an induction motor, got all the coil in there. So if you take the actual number of amps times the number of volts, that product here is 408 volt amperes. So you've got to have a lot of amps that are really not in phase. And this is called the volts amps reactive, which I'm going to calculate. This is just a simple right triangle. So if I take the 131, put it horizontally, that's real power. And then the volts times the amps, that's this hypotenuse. Right triangle, like for carpenters, you can take this squared plus this squared is equal to this squared. So I'm going to solve for the blue. So here's the volt amperes, 408 volt amperes. You can take this leg is equal to this leg squared plus this leg squared. So you've got, just like for a carpenter, 131 squared is equal to 386 squared. It's equal to this squared. So the algebra here is you've got volt amperes squared is equal to watt squared times plus VARS squared. Solve for the VARS. And you've got 386 VARS. That's for volt amperes reactive. Now if I take that and I convert it to kilovars, it's 0.386 kilovars. And now I'm going to solve for the capacitor that's needed to go ahead and force this to be to where the volt amperes is about equal to the number of watts. Get the current down. So you take this formula, kVAR times 159.155 times 10 to the 6th. That makes it in microfarads. Divided by the frequency, divided by the voltage. Plug in all this stuff. This we just calculated. 60 hertz, it's almost 120 volts. Plug all this in, you get 71 microfarads. So I've put a 71 microfarad cap in parallel with this. We should go ahead and force this blue to be way down, and the current should drop radically. From 3.4, it's probably going to go down to a little over an amp. And this is on a 3rd horsepower AC induction motor, 2-pole, 120 volts. It's a standard 56 frame motor they've made for 60 years. This motor's probably 30 years old. And my meter I use will give you the power factor. If you hear somebody say that, well, if you take the number of watts, actual power, and you divide it by the power factor, you get the number of volt amperes. And just because of the way the accuracy the meter is here, this is 409, this is 408, basically the same number. So what you want is the power factor to be 1. If the power factor is a 1, then this whole volt ampere curve will go down. It'll lay right on top of the watts, and you've got no VARs. So on industrial applications, what you do is you're metered not only on the watts, you're also metered on the VARs, because the power company has to go ahead and supply the size of the line and what they're shoveling in coal or whatever. Solar is based on amps. Same thing if you run a generator. It's based on the number of amps, of volt amps. So if you were running this motor off of a, say, a gasoline engine, it's not the number of watts that matters, it's actually the volt amperes. So if you were running this thing, let's say with a solar inverter, or you got a gas engine or something, and you say, oh, it's only 131 watts. Well, what the generator sees, it's going to see the number of volt amperes. So instead of being roughly about 1 amp, it's about 3.4 amps. And that's where you get in trouble. Now, the starting current on this is way, way higher. I'm just showing a steady state condition.